Welcome to this lesson on the Wronskian and linear independence. When we study physical systems, from swinging pendulums to quantum mechanics, we often rely on differential equations. But finding solutions is only half the battle. We must ensure our solutions are truly unique. Today, we will explore what linear independence means, why it is essential in physics, and how a powerful tool called the Wronskian determinant helps us test for it with absolute certainty. Let us dive in. Let us start with a simple analogy. Imagine you are lost in a city and ask two different people for directions. If the first person tells you to walk 1 mile north and the second person tells you to walk 2 miles north, the second person has not actually given you any new information. Their advice is just a scaled-up version of the first. We call this dependent information. However, if the second person tells you to walk 1 mile east, they have given you entirely new, independent information that helps you pinpoint your exact location on a two-dimensional map. In mathematics, we look for solutions that give us completely new information, rather than just repeating what we already know. Now that we have an intuitive grasp, let us look at the formal mathematical definition. In the language of mathematics, two functions, y1 of x and y2 of x, are tested for independence using a specific equation. c1 times y1 plus c2 times y2 equals 0. Here, c1 and c2 are just constants. We want to know if there is any way to make this equation true for all values of x. If the absolute only way to balance this equation is to set both constants exactly to 0, then the functions are linearly independent. This means neither function can be built by simply scaling or stretching the other one. This brings us to the opposite scenario. What if they are not independent? If you can find non-zero constants that make our test equation equal to 0, the functions are linearly dependent. Physically and mathematically, this means one function is simply a constant multiple of the other. Just like the person telling you to walk 2 miles north instead of 1, a dependent function contains redundant mathematical information. It doesn't add any new dimensions to our understanding of the system. In physics, relying on dependent functions means we are missing a piece of the puzzle. Why does this distinction matter so much in physics and engineering? Consider a second-order linear differential equation. These equations are everywhere. They describe the motion of a swinging pendulum, the vibrations of an oscillating spring, and even electrical circuits. The fundamental theorem of these equations guarantees that there are exactly two fundamental solutions. To construct the complete, general solution that describes every possible motion of that pendulum or spring, we absolutely must find both of these solutions. We cannot settle for just one. Building on that requirement, how do we form the final answer? We construct the general solution by combining our two fundamental solutions. But here's the catch. We must combine two solutions that are linearly independent. If we accidentally pick two dependent solutions, we only have half of the physical picture. It would be like trying to navigate a city using only north and south, with no east or west. If we do this, we will not be able to match our mathematical equation to the actual initial conditions of the real-world system. Our model would simply fail. Since having independent solutions is so critical, we cannot just guess. While it might be easy to see that sine and cosine are different, more complex functions can easily trick the eye. We need a reliable, mechanical test to check if our two solutions are truly independent. To avoid guessing, a Polish mathematician named Józef Maria Honi-Wronski developed a brilliant mathematical tool. He found a way to transform the abstract question of independence into a straightforward plug-and-chug calculation. This tool gives us a definitive yes or no answer every single time. Here is the mathematical tool Wronski developed. The Wronskian is a special determinant constructed using the functions themselves and their first derivatives. Let us break down the symbols. W represents the Wronskian. The terms y1 and y2 are the two functions we are testing, placed in the top row. The terms y1 prime and y2 prime are their respective first derivatives with respect to the variable x, placed in the bottom row. The vertical bars denote the determinant of a 2x2 matrix. To calculate it, we multiply the top left term by the bottom right term, and then subtract the product of the top right and bottom left terms. The resulting expression is our test. If w is not equal to 0, the functions are linearly independent. If w is exactly 0 for all x, they are dependent. Now that we have our formula, let us see it in action with a concrete example. We will test two functions that frequently appear in physics problems involving damping or growth: e to the power of 2x and e to the power of negative 2x. First, we find the derivative of each function using the standard chain rule, bringing down factors of 2 and negative 2. Next, we set up our Wronskian determinant with the original functions on top and their derivatives on the bottom. We expand this by cross-multiplying the diagonal elements. Notice how the exponential terms interact. When we multiply e to the 2x by e to the negative 2x, the exponents add up to 0, leaving e to the 0, which is just 1. We are left with negative 2 minus 2, giving a final Wronskian of negative 4. Because negative 4 is strictly not equal to 0, we confidently conclude these functions are linearly independent. Physically, they represent completely distinct behaviors, like exponential growth and decay. Let us try another classic example, this time from the physics of waves and oscillations. Suppose we have the sine of x and the cosine of x. We intuitively know these are distinct, but let us prove it mathematically. First, we compute the standard calculus derivatives. The derivative of sine is cosine, and the derivative of cosine is negative sine. It is crucial to remember that negative sign. We populate our determinant matrix and cross-multiply. This gives us a product of sines minus a product of cosines, specifically negative sine squared minus cosine squared. By factoring out the negative sign, we reveal the classic Pythagorean identity. Sine squared plus cosine squared equals 1. Therefore, our Wronskian evaluates to negative 1. Since negative 1 is not 0, the sine and cosine functions are linearly independent. This proves they provide unique, non-redundant information, allowing us to describe any oscillatory motion. To truly cement this idea, let us look at what linear independence means visually. Here we see a graph of the two functions we just tested, the sine wave in solid blue and the cosine wave in dashed red. The horizontal axis represents our variable x, which could be angle or time, and the vertical axis is the amplitude. Notice their zero crossings and peaks. The sine wave starts at 0, while the cosine wave starts at its maximum of 1. You cannot simply stretch or shrink the blue curve vertically to make it perfectly match the red curve. Because one is not a scalar multiple of the other, they are fundamentally different shapes in this context. This visual phase shift perfectly aligns with our Wronskian calculation of negative 1. Together, they form a complete basis to describe any wave. We have covered a lot of ground, So let us summarize the most important ideas. First, linear independence ensures that the mathematical building blocks we use are truly unique and not just redundant copies of each other. Second, when solving higher-order differential equations in physics, finding independent solutions is mandatory to capture the complete physical picture and match real-world initial conditions. Finally, the Wronskian provides a simple, elegant determinant test to verify this independence. By checking if the Wronskian is non-zero, we guarantee our solutions are robust. Mastering this tool is a crucial step in confidently solving complex problems in mathematical physics. You now have the foundation to test any set of functions you encounter.